And welcome back to another episode of Try Again Dev. Today we are going to be trying to take a look at some graph problems for the first time. So I'm just going to fiddle with getting the chat up and running, and then looking forward to getting engaged with y'all, or whoever might choose to join today. Gonna get LeetCode, and I'm gonna be sharing my screen momentarily. Thank you for your patience, friends. Guess not. It's okay. Excuse me. So let's get it going. Alright, so thank you so much for joining if you're here or watching later. This is Try Again Dev, where we know that we don't learn just from being born, we have to learn stuff. It takes us time, so we have to try again. So today we're gonna try again, at least try to get some basic principles of graphs going, and see what we could do until we can solve a graphs problem. So gonna transition to a screen share here, and let's go ahead from there. So let's pick a graph problem. So up to now, the goal's kind of been getting through the easy problems. That said, I have a mock interview on graphs, so no better way to learn than by doing. Okay, so we have a lot of questions. They're all medium. Except this hard one, so we're definitely not going to do that. So I did see a walkthrough of this question, which is number of connected components in an undirected graph, and I think that's probably a good place to start. So let's do this one today. So here's the problem. We have an undirected graph with n nodes. They're also edges or edges array.length, great edges, where some value I, or like the item at that index C, is A and B, which is saying that there's an edge between them. So the nodes are numbered from 0 to n minus 1, so each of the nodes are identified as a number. Okay, so that this graph's going to have numbers. Okay. Return the total number of connected components in that graph. All right. So let's check out our time and space complexity. It looks like both of them are v plus e, where v is vertices or nodes and e is edges. That makes sense. Essentially, it means we can loop through every item in the array. In terms of time, we can do that multiple times. And we can store every item in the array, which makes sense because we're probably going to have to make like a lookup tree for our problem. So yeah, like let's see some of the things that I might make as assumptions, or check with the interviewer, depending. Also, I'll try to remember that we have the chat open, so I'll try to put paint here more centrally. But I do still want us to be able to see the problem statement if we can. Please. Okay, and let me bring back up our chat so I'm sure that, not writing outside the lines too much. Let's check our viewport here. Yeah, for some reason this stream chat is like not cooperating today, but that's okay. I'll try to keep it to here, and it looks like that should be all right. Okay, let's get back to it. So let's write down some of the things that we think we'll have to do. So we have an underacted graph with n nodes, so we might have something like 0 goes to 1, goes to 2, goes to 3, goes to 0. And we need however many connected components. So then we might have like 4, 5, and that's like a different situation. So one of the things I've learned is breadth first search goes by layers, right? So if we start here, then this would be in our first layer, and this would be the next layer, and then this wouldn't be counted in there. But like, we don't need anything like that that's like layered like that. So since we are trying to like essentially go around this shape and like see what there is there, and then we'll have to go around whatever's left, that means that we should maybe consider, sorry, breadth, or excuse me, depth first search approach. Okay, so we know that. The next thing, like, let's plan for how we're gonna solve this problem. We're gonna need a counter, which is gonna like return at the end for like how many shapes we get through. Another thing we're gonna need is gonna be, sorry, I'm just getting a text message, so I'm making sure that my phone's flashing. Yeah, so we're gonna have to need a counter. We're also gonna need like an adjacency list. And that is pretty much like an object or a set where the key is the points that we're at, or the node that we're at, which maybe I should just write nodes that we're keeping all the vocabulary the same. And the values are whatever like children or connected edges, e's. So that's something we need as a thing. We need this counter. We'll need this DFS function so that we could see like where we are, where we're going. And then like we'll probably pass it in starting at this item. Let's see what we want it to do to see if we need anything else for storage of stuff. So what we'll probably do is, and remember, depth first search goes all the way down something, like to the deepest end, and then it like comes back up in little parts or pieces, right? So if we start at this 0 right here, we're gonna go to 3, we're gonna go to 2, we're gonna go to 1. Like, and this is like the deepest place we can get without revisiting where we are, right? So like another thing we'll probably need is like a visited array. So that way we're like, okay, we're at 0, we're like evaluating 0, great. So like, hey, we're gonna say what is 0 connected to? So we're gonna put that in the adjacency list. So we'll say 0, and that's connected to 1 and 3, great, okay. So that what? It's funny. I mean, I guess at the points we visit along the way, we can like put those in the adjacency list. So like if we did that 3, we'd have connected to 0 and 2. 2, we'd have connected to 1 and 3. 1, we'd have connected to 0 and 3. Okay. So like I'm in two minds here because like okay, when we visit all these nodes, we will not have visited everything in the adjacency list if we build the adjacency list first, right? So I'm like, should we do that first? Like I'm just ordering the thoughts here. Like we'll do making the adjacency list first, right? So then when we go through and like analyze this portion of things from the adjacency list, we would do like adjacency list minus evaluated. We would have to, at the end of this series, plus 1 to the counter. I'm guessing we can like remove them from the adjacency list. And then we like proceed with whatever's left in the adjacency list, which like I'm assuming is like we visited 1, we visited 3, we visited 2, we visited these 4 nodes. And then we're like, okay, now we have in the adjacency list 4, 5, and 5, 4. Those aren't in the visited array, so we'd have added this to the counter. As we start evaluating this, we do our counter plus 1 again. Then we visit 4, 4 is in 5, 5 is in 4, great. I've seen in some of them they have like a parent feature, so that way you're like tracking where you came from. So like in a case like this, you won't create an infinite loop. But yeah, I think with this information, it's like we have a plan, and like now it's time for trying to write the code. So that way, if we do or don't know, we can get at least a bit of practice with trying it out. So let's do that. We said we would want to have a DFS function. DFS. And what would this take in? Not really sure yet, so we'll come back to that. We'll have a counter, let counter equal 0. We'll have an adjacency list, let adjacency list equal this situation. Great. All right, so what's n? Number of nodes? Okay. So like here we have 3 nodes, 0, 1, and 2. Then edge from 0 to 1, 0 to 2. Okay, here we have 6 nodes, 0, 1, 2, 3, 4, 5, and 6. Yeah, the nodes are at 0 to n minus 1. Excuse me, and then, yeah, sure. So, okay, let's first populate our adjacency list, right? So we have to loop through all items and edges, build our adjacency list array. Yeah, because it's going to be like a key value pair with the key being the number and the value being the array. So, all right, let's just write it and figure it out as we go. So for let I equals 0, I is going to be less than n, and we're going to increment I every time we go. So the first thing we can do is populate the values or the keys with an empty array. So we could say adjacency list dot push, and then I. That's going to be the key. I think it's like this is what we want to push there, and then this is the place we want to push it. So like we don't have adjacency list I existing, so we're going to push an empty array into there. So let's just do that and console log the adjacency list to start off with. Sorry, I do this by seeing, so that's what we're going to do. So adjacency list. Oh. Wonder if it'll be like equals. Okay, fantastic. So we've made this empty situation. Great. All right, great. For all the items n we have. So then now we're gonna loop through again, going through the edges. So like we're gonna make another for loop here. And then this is gonna be edges.length. Okay, so like for each item in the edge. Let's see. So I think it'll be like for a v of edges I. Let's see if this will let us do something like that. Okay, cool, perhaps. Right, because this is like a two-value situation here. We're going to say adjacency list A dot push B and adjacency list B dot push A. That should create our adjacency list, or populate, I should say, our adjacency list. So let's see if that works. I wonder if we have to like say let. Okay, so we're gonna do a bit of research here. Assume there are no edges, blah blah blah. Use DSU, union find, not really sure what that is. Okay, sure, no. I'm gonna look at, ooh, I didn't know you could write notes in here. All right, we're gonna do JavaScript. I'm just gonna scroll down until I could see how they do this bit. Okay, so it looks like instead of like let or something, we have to set this as a constant. So let's try that. Const blah blah. Oh, it has to have hard brackets, I guess, because it's in an array, even though it's like. Oh, right, okay, because I guess it's an array of arrays, sure. Let's see if that works. For is not iterable. What? For constant blank blank of edges. Okay, so maybe we don't need that it's like of edges I, or like in a for loop that way, I guess. It's just for this item in this thing. Let's see if that works. Just go in directly with what they want. For some reason it really doesn't like, oh, I'm outside of the, must have deleted an extra. Trying to see there. Sure, take it. Okay, that's great. Yeah, so now we have successfully derived our adjacency list. So let's see what we wanted to do first. We have our adjacency list, we have our counter. Awesome. Thank God, okay. So I think what we're gonna have to do is pass into the DFS function that we threatened to write, the like node that we want to like evaluate, right? So like when we start, let's see, who do we want to pass into here? Do we want to pass all the nodes in? Do we want to pass, like for DFS to call itself on the children of the first node we pass in? And then if the adjacency list is not empty, then we can pass in any children. Okay, so I'm like thinking aloud here. Like if the adjacency list is not empty, pass in first node that's like left. And then well, we're gonna have to first start by like passing in the 0th node, right? So here we're gonna call DFS on 0 because we always start at 0. Is n always gonna have a value? Like, are they always gonna pass us nodes? Yes, okay, great. But there might be no edges, that's fine. So we're gonna call DFS on node 0. What are we gonna do with this? So we set it 0. We see that its children are 1 and 2 in this case. So they have like 0, 1, 2. You'll definitely want to run DFS on the children if they're not in the visited array. So like let visited equal this other set. We're gonna push first this into the set there, visited. So visited dot push node. Great, that's one thing dealt with. Then what are we gonna do? We're gonna go to the children or let's say child of whatever we're at. So that would be adjacency list of the node that we're at. Let's console log child for now. Also, what is our base case here? Or let's see. So if we have not seen this node, okay, so if node in visited, we'll definitely want to just, do we want to return anything? Like what are we trying to do here? Here's an undirected graph, blah, blah, blah. Okay, at the end of the DFS function, like if we've achieved all the children or whatever, we're going to increment the counter. So that's the point of this. If the node is in the visited array, we're going to continue, aka bypass everything. Oops. Symbols here. If it's not in visited, we're going to put it into visited. We're gonna, for the child of the adjacency list node, we're gonna, I mean, yes, we're gonna console log it, but like ideally we're gonna run DFS on it. DFS child. Yeah, and when we run DFS on all the children, like essentially we're just like gonna visit it. Like I want, like, okay, so we had talked about maybe deleting these or something. Yeah, I like that idea actually. So after we visit that child in the adjacency list, we could take it out by doing unshift. No. So when you shift everything back or forward because you take it out. And unshift, yeah, you squeeze everything else back because you're putting something in. So we're gonna take it out. So we're gonna remove or the well, I mean the other thing we could do is we could like leave it alone here. And then when we're done evaluating all the children, we can just remove it from the adjacency list. So for child adjacency list node, so like if we go through boom, boom, we took out all the children, now we're done with the for loop, then we can say like, how do we remove something from a dictionary? JavaScript from dictionary. Go Geeks for Geeks in advance, right? I'm guessing they're gonna tell us how. Ooh, stack, okay. Scylla making a comeback. Okay, we just delete the key, I guess. Yeah. Cool. Let's do that. Alright, so then this is going to be adjacency list dot delete, then node. Alright, because if we're at the node like 0, putting 0 into the visited array, we're going to evaluate 0, evaluate 3, evaluate 2, evaluate 1, because we're calling this on that. And we're deleting these items from the adjacency list, right? This counter plus plus. And then if I'm like, if the adjacency list has anything in it, adjacency list does not equal this empty set, then we're gonna run, oops, then we're gonna run this on whatever is in there first. So DFS adjacency list 0, and then let's see what breaks. I wonder if I can return. Visited.push is not a function. Oh, well, like, I think it's because I made it an object, yeah. Let's make it a new set. Fix that. I wonder if it's like .add, because it's a set. Guess we have to use let to define the child here. Oh, shoot. Okay, well, we definitely hit a roly-poly roundabout. Because 0 points to 1 and 1 points to 0. Alright, I'm running out of the time I have for today, so let's look at how our solution is supposed to look and revisit this problem another day. See what we got, see what we're missing, etc. So, okay, we had a counter, which, oh wow, they actually did a breadth first search way too. Yeah, that means I'm supposed to be somewhere else, unfortunately, so. Alright, array.from, great, we did this, we did that. For neighbor adjacency load, if we have not yet visited the neighbor, then we can visit them, and then we run DFS on it. Okay, so they did the check like here if the neighbor was there instead of in the function itself. Got it. They have this res counter result. If the node is 0 to n, if we have not visited the node, we visit the node. Oh, I see, okay. Okay, so here's the function, and then they loop through the full adjacency list instead of doing this like delete situation. Okay. Well, hey, next time we see a problem like this, hopefully we get a little further. That's today's episode, just going ahead and showing that sometimes you gotta just try again. So looking forward to trying again with y'all soon. Have a good one, and keep steady learning. Remember, practice makes progress. Only perfect practice makes perfect. See y'all next time. Bye.